Hello everyone. In this video we're going to talk about different cost functions in TensorFlow, and I'm not going to go through all of them, okay, and I have not collected all of them, but these are the major ones, the major categories. So there are some other ones too that are closely related to these, but I would say these are the major ones, and these are probably like 70–80% of them that I have collected here. So the first three are the ones that you use for regression, and these are mean absolute error, mean squared error, and Huber. So MAE and MSE, they are very common, and you probably have seen them elsewhere too, where you subtract the correct value or the real value, the sample value output from the predicted value, yi minus y hat I, sum all of these error terms, and then take the average by dividing by the number, or you can square these error terms and divide it by the number, okay? Now, when comparing this to MAE and MSE, MAE is less sensitive to outliers. It does not punish the errors as much as the squared method does. Here, the error is raised to power 1, while here is raised to power 2. So the MSE method is more sensitive to outliers, okay? But it does not have too much of oscillations that the MAE does. Plus, MAE, remember, if this is your cost function j and you want to take derivative with respect to some parameter that was used in this y hat, you are taking derivative of absolute value function, and you know derivative of the absolute value of x with respect to x, because the absolute value function does not have derivative at x of 0, right? So if you remember, this is like x over absolute value of x, or absolute value of x over x, which has discontinuity at 0. Okay, on one side it goes to 1, on the other side it goes to -1. So it's not such a nice function when it comes to taking derivatives of that. But the square term, when you take derivatives, you're going to get linear terms, and that is very easy. And so each one has advantages and disadvantages, and one way that you can take both of the advantages and combine them is using this function called Huber loss function, which is combination of the two. As you can see, if the amount of error is less than some predetermined value delta, it is using the square function, and otherwise, if it's bigger than that, then it is using the linear form. And the fact that you have subtracted this 1/2 delta and multiplied by delta to make this function continuous and to make it have derivatives. But the goal is, again, when the error is small, you go square. When the error is big, you go what? You go linear. Okay, so that's the kind of behavior, and it is a quite bit, I would say, useful functions for regressions when we want or we expect to have outliers and we don't want to have the behavior of MAE. So the next one is called the Poisson's loss function or cost function. It is good for problems that have count data. In other words, the outputs are non-negative integers, like you want to count how many numbers have visited a website in a day or the number of words in a document. So if you have a deep learning task that involves stuff like this, the output is non-negative integer, then Poisson, and the data are coming from a Poisson distribution. This Poisson loss function is quite useful, and you can see that it is the predicted output minus the basically desired output or the target times log of y here. The third one we're going to talk about is for classification problems that are only binary. It means there are two classes, either class 1 or class 2, either true or false, either 1 or 0, something like that. So the output has to have a sigmoid function, And in this case, and I mentioned it in one of my machine learning videos under playlist machine learning, the binary cross-entropy is the cost function to be used here. Again, y is like the t, is the target value or the expected value, and y hat is the predicted value. And so you see, this is basically the entropy between one class and its predicted, and this is the entropy between the other class and its counterpart, predicted part. Okay, and you add them and divide it by n with the negative sign to make the whole thing positive. Because these y's and yi's are zeros or ones or between. The yi's are 0 or 1 in general, let's say, and y hat is a number between 0 and 1. Okay, because it comes from the sigmoid function. Okay, so this yi, as I said, let me write it for you. It is either what? It is either 0 or 1, but this y hat I, since it's coming from a sigmoid function, it is between 0 to 1. Okay, now if instead of classifying between two classes, you have several classes, multi-classes, where the output layer is a softmax function, which I showed you in one of my previous videos, then you want to use this cost function called categorical cross-entropy, for which the cost function is shown down here. So again, here you have those t values, right? And you have the predicted values. And here you have to take a double summation where index I is for sample index and index k is for class label. And yik, these targets, are one-hot encoded values. And if you look at my previous video, I explained one-hot encoded value. What does it mean, right? So it's converting those numbers basically into a bunch of zeros and ones, where only one of the values is 1 and the rest of them is 0. It's an inefficient encoding basically, but this categorical cross-entropy uses that, and it can work fine. Again, here, this yik is, it could be integer or non-integer in general, and these numbers are probabilities that are coming out, okay, coming from a softmax function. Now, if these yiks are definitely integer numbers, so you have encoded your classes or labels of the classes with like 1, 2, 3, just integers, then you can use this method called Sparse Categorical Cross-Entropy, in which this yik, which is something like, let's say, 0, 0, right? Then another 0, and then a 1. Let's say you have 6 classes, okay? And the class that you have for this specific one is class 4, right? So when you multiply these zeros by log of the predicted values for them, regardless of whatever this log of y hat ik is, when they are multiplied by 0, you get a 0. So the only one of these y hat ik's that is used is the fourth one, which is multiplied by 1. The rest of them will literally be multiplied by 0. They are useless. So in this sparse method, it is neglecting all of this, and it is only using that single 1 value. Plug it here. It knows it's a 1, so you don't even need to use it. And so it only basically uses this second portion of log. Okay, and it can even get rid of one of the summations, so the formula becomes much simpler. So if you have integer for the labels of the classes or the targets, then you might want to use this sparse categorical cross-entropy, which is faster and is not as computationally expensive. Now, sometimes these classes that you're trying to separate from each other and classify, they have some data that, or some samples that are easier to classify, and they have some samples that are harder to classify. Okay, so there are some boundaries between these classes. Some data are very close to the boundaries, some data are far off from the boundaries. So those that are far off, you can easily classify. But the ones that are close to the boundaries, to the real boundaries, they are harder to detect. So that is what we call class imbalance. And you can see that in problems like object detection, right? When you want to detect an object against a background, the pixels on the boundaries of the object, they are not so easy to detect most of the times. So in those cases, we use another version of this cross-entropy or categorical cross-entropy, which is called categorical focal cross-entropy. This one, it has this cost function on the right, and here, if you look at it, the cost function is a little bit different. Here, this PT, okay, which is the true output, or it's the same as the T, it is going to be equal to the prediction if that class is 1, and this is here just for 2 classes, but you can extend it to several classes, and it's equal to 1 minus y otherwise. And the cost function you are trying to minimize is negative 1 minus pt to the power gamma, which is a parameter of this, this cost function, times log of pt. So again, it's an entropy, but there is this power gamma in it. If this power gamma is equal to 0, then you are just looking at what? You are just looking at that sparse one. Okay, remember I told you in the sparse one, you are just looking at the log of p, right? So if gamma is 0, but this gamma is typically not 0, and it's somewhere between 0 and 1, okay? And this parameter, we call it a focusing parameter. It allows for this cost function to do what? It allows for it to give a smaller weight to the samples that are easier to detect, and give it what? A bigger weight to the ones that are harder to detect. Okay, so they all kind of contribute the same to the cost function, not differently. Okay, so again, the harder samples to classify, they get a bigger weight. The ones that are easier, they're gonna get a smaller weight. So this way we can kind of get rid of that imbalance in the class, and basically we perform the job. Okay, the next one is called a hinge loss. A hinge loss is also used for classification, but like support vector machines, this is the cost function that you use in support vector machines. It is good when you try to maximize the gap between the 2 classes or several classes. Okay, so if you have a bunch of samples in this class and you have a bunch of samples in the other class, you know, if you use a perceptron, and I told you in the past, if you want to use a perceptron, this perceptron gives you a hyperplane, and it could be this one, it could be this one, it could be this one, it could be this one. All of them can separate these 2 classes, right? But which one of them will give the maximum gap, or it's exactly in between the 2? Then that's the job of support vector machines, which come and say probably this one. And then these data that are on these lines parallel to this hyperplane falling on it, these guys, we call them support vectors. Okay, I have a video on my in my machine learning playlist. It's called Support Vector Machines Theory and Application in MATLAB. And I have another one that I did support vector machines in scikit-learn. So I have covered this support vector machines. The cost function for it is basically this hinge function, which is maximum of 0 and 1 minus t times y. Again, y is the prediction, t is the target value. which could be, in this case, +1 or -1. So you see, when you do the support vector machine, one class will get the one of these boundaries will get t of -1, and the other one will get t of +1. Okay, and it's not like 0 and 1. So the goal of this cost function to use is to maximize this gap, okay, this width here, or this band, you might call it. Now, sometimes you have more than 2 classes, and with 3 classes, you want to find 3 hyperplanes that have the maximum gap between them. In that case, you use the method called categorical hinge. So in TensorFlow, categorical typically is used for multi-class scenarios. Okay, if you have multi-class scenarios, instead of a binary cross-entropy, you use a categorical one, and instead of a hinge, you use what? A categorical hinge. The last one I want to talk about is called the Kullback-Leibler Divergence, okay, or KL divergence, which is basically a type of entropy. You might call it a joint entropy between 2 distributions, P and Q, that are defined over events X, and it measures the difference between these 2 probability distributions, one of them P, one of them Q. So if you have 2 distributions and you want to see how close they are, you calculate this joint entropy formula, this divergence for them. If it's 0, that means they are identical. You see, if P and Q are the same, this ratio will be 1, log of 1 will be 0. If they are different, then this number will be bigger than 0. Okay, so this number is bigger than or equal 0, and again, if it's 0, means they are the same, the identical distributions. Now, where would you use this in machine learning or deep learning? One of them is to detect drift in data sets. Like, datas are constantly changing, and you need some way to see if this change is significant. For instance, you want to see whether this data that you have they have changed enough, so you need to retrain the system. For instance, let's say we have trained a system to detect what kind of videos the people are more likely to see. So I can put it on YouTube or somewhere else, or what kind of ads the people are more likely to see, okay? And based on that, you might put that ad on Facebook or elsewhere. And now something changed in the society, like Corona came or something else, and now the people don't have the same interest that they had a year ago or 2 years ago, because, let's say, the economy changed, or the people are under depression or pressure, or so many other things, okay? And so now you might need to change the type of ads that you're showing to people. You might need to retrain your network that are suggesting these ads or suggesting these videos, or the younger generation are now more looking at them instead of maybe a little bit older generation. So this one will help you to see whether the probability distributions of those videos you suggested or the ads compared to last year, if it has changed significantly, and if it does, then you have to retrain the system. Another one you can use it is in general adversarial networks, or GANs, which are used to create fake data from some real ones. Okay, that's one of their applications. And in one of my future videos, I'm gonna go over GANs because I think they are interesting networks. So you have 2 networks competing each other. One of them is trying to basically create a fake version of something real, and the other one is trying to distinguish that, okay? Again, I'm gonna go over them later, but you can use the KL divergence here to have what? To basically try to maximize the divergence matrix, that discriminator, the one that is trying to find if there is anything fake. That guy is trying to maximize this divergence. The other one is trying to what? Minimize it, the one that is trying to generate the fake. The generator network trying to minimize it. Minimize between what and what? Between the fake, let's say, picture and what? The real picture. And what kind of distribution are we talking about? Let's say distribution of what? Distribution of colors in the pixels, distribution of whatever. This P and Q, you can define them, what attribute of the image you're looking at, and you're defining P and Q over, right? It could be so many things. So you want to see, let's say, if the distribution of color, if the location of the pixels or whatever, the entropy, skewness, so many measures in the picture, contrast, if these distributions of the fake image and the real image are very close to each other or not. The generator networks tries to minimize it so they are not distinguishable from each other. The discriminator network tries to maximize it so it can detect the fake from the real one. And then in order for both of them to work, you need a min-max loss configuration using the KL divergence. In natural language processing, one application could be, let's say, if you want to classify different types of documents based on their topics, right? You can look at the distribution of the words or the randomness of different words appearing in them, right? So if you have a bunch of documents that are all technical, and then you have a bunch of other documents that are, let's say, what? Like, for instance, children bedtime stories, then you look at the kind of the words that appear in them, and that will help you the distribution of those different words that you see in these books. It helps you categorize this new book that you're looking at as whether what? Technical or like a bedtime story, right? So if you see a lot of once upon a time instead of like computer or something like that, that is an indication. In reinforcement learning, you can also use it to penalize a new policy from being too far from a previous one. Okay, so it has applications in lots of things, in basically in distinguishing fake from real, categorizing documents, drift in the data sets, in reinforcement learning, and so on. The last thing I want to mention is it has a little bit of limitation too. It's not like perfect. One of that is it's not symmetric. What does it mean? It means if I change P and Q, so if I calculate divergence KL of Q and P, so this guy becomes Q and that guy becomes Q over P, right? Then guess what? The results are not the same. Okay, and you can show that that DKL of PQ, okay, and QP, these are not the same thing. These two are different results. And so that makes this measure to not be a perfect distance measure, because the distance between two things does not depend on which one you go put first, the other one second. It has to have a commutative property, right? Distance between point 1 and point 2 is the same as distance between point 2 and point 1. This one is not. These two, as I said, these two are not equal. So that's one of the problems that you have. Okay. And the other thing is, if the data samples that you have here, if these data samples are pulled from distributions that have different parameters, then this is not going to work very beautifully. Okay? Yes? So if you have one distribution, let's say this P and Q are basically coming from a normal distribution, a Gaussian distribution, but from these distributions, they have different mean and different variance. And now we are trying to see if they belong to the same thing or not. Well, guess what? You're not going to get a good result, and it's not super reliable, okay? So it has some limitations, and we need to be careful. There are other divergence metrics, and I don't want to go over them because as far as I've checked, we don't have them in TensorFlow, but there are other metrics. And if you want, you can, by the way, in TensorFlow, you can have custom cost functions. Okay, so they are not all pre-built. You can define your own, and in one of my future videos, I'll show you how to define a custom cost function. Okay, and so if that's the case, then you can define other kind of cost functions like a divergence that is symmetric, and you can rely on it more, or you can define other kind of cost functions for regression or classification. And again, I'll cover that in one of the future videos, but these are the ones that are most commonly used, and they are available in TensorFlow. They are coded already, so you can use them. Okay, hopefully this video was useful to you. I'll see you in the next lecture. Thank you.